So before I move on from my title slide here, I'd love to point out NGC 128 here in the background, which has a really beautiful X. This is kind of the first X in the edge-on galaxy kind of discovery. So I'm going to use that as my background throughout the talk, but just to kind of give you an idea of what we are talking about. That is an X in a galaxy, and this is what these structures look like in the universe. So first, a little background. X's in bars. These are also called kind of boxy peanut bulges, Barlin bulges, and they contain that X-shaped morphology that we just talked about. You can still see it, small right there. So these are described as vertically thick structures in the central parts of disks where there is an excess of light above the disk. They're challenging the assumption that most of the mass will reside in the classical bulge, as Hortail, Gerhardt found that these X structures can account for like 40 to 45% of the mass in the stellar mass. So these are really, really important structures that are different from a classical bulge. They occur in like bright, isolated Milky Way mass galaxies with about half of S0 to SD galaxies containing these boxy peanut bulges, it's looking like. So once again, these are not classical bulges formed early by accretion events. They're not supported by velocity dispersion, and they're not disky pseudobulges. So just kind of really give you an idea of what is an X, what am I talking about here? These X-shaped morphology, boxy peanut bulges are all kind of this one category of things that are not classical bulges and are not disky pseudobulges. Okay, so observational evidence for them. I've already talked a little bit about NGC 128. So it was observed with this boxy bulge, which was then later resolved to have this distinct X structure. Large majority of boxy peanut bulge structures are found to be associated with bars, which is why I'm calling them X's in bars, because they are associated with bars. And here I'm showing, I can't walk away from that. Here I'm showing a series of 3 images that kind of illuminate the kind of variety of these X structures and how they can be. So the top one, you can see that the X meets in the middle. And the bottom one, you can see the X doesn't quite meet in the middle. So this is just to show that these X's can have different morphology. This is from a sample of 30 edge-on disk galaxies, which they extracted these central X shapes by doing a median K in band filter. So they kind of pull out these sharp structures is the idea of this filter. So you can really pull out these X bar structures that you might not see in the initial image. But what's important here is that they don't have to meet at the center. You can have these non-centered X, and you can have a centered X, which looks really like an X. There's kind of a variety to what these can look like. So we have observational evidence. We see these, all over in Milky Way mass galaxies, especially, which is, especially interesting for us. We see them in the Milky Way. There's evidence for the X in the Milky Way center. So now how do we kind of learn more about this? We move to simulations. So the first simulation model that I want to highlight here is Athanasoulia's 2005 simulations. That whole figure on the far right of your screen is a series of the images from the simulation. They predict key features of the boxy peanut bulges in addition to just, you seeing it there, obviously, in that image. Other simulations that I also want to acknowledge that do produce these X features can have them happen with or without buckling occurring. So that's something that you may have heard about being associated with these X features. I will talk about buckling briefly in a second. But it's just important to show and note that in simulations of all types, these X features do pop up. So we see them in observations. So observationally motivated, we know to look for them. And then we see them pop up in simulations as well of disk galaxies. So the simulation specifically that I worked with for the last couple of weeks is the simulation by Jason Hunt in this room with many of his collaborators who are also in this room and out of this room. This is a 270 million disk particle, 1 billion dark matter particle simulation. It's a gigantic simulation. You heard about it briefly yesterday for those who were here with the version where there was a satellite that comes through and disrupts it. We are using, in my work, a version that does not have a satellite. You can see in the middle there's the beginning of that X structure starting to pop up. And so the simulation is really powerful because it has so many particles. But I do want to acknowledge that having so many particles is a really amazing thing because we can learn a lot from this. But there's a lot of value in that. But it also led to a really big computational challenge that I spent maybe a majority of my time here actually kind of tackling. So I'm not going to talk about that much in this talk. Happy to talk to you about it offline. It's not the science, it's the nits and grits of doing the science so we can do the science. But I did spend quite a bit of time making it so we could actually trace individual particles in this gigantic simulation very efficiently through the whole simulation, and also wrote code that made it so we could load the individual snaps differently and things like that. So there was a big portion of my time was kind of spent in enabling us to do the science and not necessarily doing the science yet. But now we have a whole bunch of tools that have made it so we can do some really interesting things and ask some really interesting questions. So those questions that we want to ask, right, kind of start with like, okay, where are these X's coming from? And so I'm going to outline the proposed formation mechanisms real quick. So first I mentioned buckling. Buckling instability is this initial distortion has to happen from the vertically trapped limb-bound resonance 2-to-1 stars. And so these is F, you see FZ, so FC to FX. That is the frequency in the vertical orbits and compared to the frequency of the orbits in the plane. So of a single star, you're going to look at its component in the Z direction and its component in the X direction. If you take those stars that are being disrupted there, you have the buckling instability. The 2-to-1 banana orbits, which are the 2-to-1 limb resonance that I am referencing, these guys have been proposed to be responsible for stimulating a buckling instability in some galaxies and in some simulations. But I do want to also point out that you don't have to have a buckling instability to form it. As I mentioned before, you don't have to have buckling to happen to get the X structure. So one proposed mechanism that doesn't require buckling is that these bezel orbits, so this is a family of bezel orbits as described in detail by Portel, Weg, and Gerhard in 2015. These bezel orbits are not 2-to-1 in the Z to X, but are lower than that, but higher than like 3-to-2. So these kind of end up looking like this. This is in the bar frame. So keep in mind, you're looking at it as if the bar were oriented perpendicularly to you. And these bezel orbits form kind of a structure that supports that boxy structure that you're seeing in the center. And then you can take the 2-to-1 banana orbits, which are going to be like little bananas like this, and those kind of can extend beyond the central structure, which leads to the boxy X. So that the presence of these orbits and the number of them does not require that the buckling instability occur and happen for this X bar to actually pop up. So now we have an idea of like what these might be, where they might be coming from. So the next step was to go into the simulation and actually identify the X bar stars. So it's identifiable, by eye. It's pretty much what I've been saying this whole time. Every time I point it out, like look at this background, you can still see NGC 128 on there. You can see the X, right? But that doesn't actually tell you how to grab the X. So what I did is I just said, I don't need to do anything super fancy. The X is there. I know it's there. This is an observationally motivated problem. So I'm just going to grab the stars that look like they are in the X and then ask questions about them and learn how to characterize them. So I made a selection in the edge-on orientation. So we moved into the bar frame in every single frame in order to make the X bar selection. And I basically just said less than 2 kiloparsecs from the disk and symmetrically around the kind of quantiles, quarters of the frame. I made a selection that way, and then also a selection in the plane this way, like above the bar. So this is how I selected the X bar particles. These numbers are motivated somewhat by some selections that were made in other papers like Portel, Weg, and Gerhard, but they were also kind of arbitrarily just made based off of what I could see in the simulation. Once we have those particles, we then want to actually ask the questions we were asking. What are these particles? So we're going to first look at what is the orbits of some of these X bar particles. And first I'm going to start with the banana orbit that I've been mentioning over and over again. So here is an example of a banana orbit. This was selected at 4.2 gigayears in the simulation, so well after the bar formation, which was around like 0.8 gigayears. You can see This is in the bar frame, so we really have that banana structure there. In the far bottom left plot over here, this is the Z to X. I do want to then point out that the top right plot is the Y to X, so that's looking from above. You can imagine that the bar in that is oriented just, along 0 and Y, perpendicular to that vertical axis and, horizontally parallel to the x-axis. So this is the same orientation that we will use for all of these plots. I'm going to show a couple more of these, so I want to make sure we're oriented here. Bottom right plot is RVR, so that allows you to kind of by eye look at it and say, oh, look, wow, resonances. Something fun's happening there. Things are, exciting. So this is the plot that I've chosen to show. And then we have our orbit in the upper left, which is just the three-dimensional orbit over time. Color bar is time for the same in all of those with the dots corresponding to the upper right color bar. So for these 2-to-1 banana orbit, I specifically selected these by just essentially going through and asking, okay, we've looked at 4.2 gig years, I've selected the X bar, and then I said, okay, now give me 100 mega years. 100 mega years, no, give me a giga year. Sorry, I want to make sure. Give me 1 giga year and tell me about the orbit in that time period. And what I asked it was just, how many apocenters do we have in Z? How many apocenters do we have in R? And then just take the ratio of them. And this is one where I had a 2-to-1 ratio. That's how I selected this. I have a whole family of banana orbits like that. I then asked, okay, I also want to grab the bezel orbits. So I just said, give me 1.5 to 1.9. Here's 2 of those, nice examples. Same selection criteria, same procedure, same plots. So once again, you're looking at the projection from top down in the top right, and then you can see the actual kind of selection criteria in motion in the bottom left of each of those plots. You can see that X structure popping right out. These bezel orbits do a really good job of looking like X's, so this seems really promising to kind of look at these different characteristics and look at these different orbits. So once we have these orbits and I have large number of these and I've selected them over many different times and I've asked what those look like at different times throughout the simulation, I'm not going to go into those details here because I don't have conclusions about any of that yet, but I will show kind of a preliminary analysis of characterizing the X-bar particles. So the way that I talked about on the last slide, we're at 4.2 gig years. I selected the individual X-bar and then looked at the orbits around that time. Do the same thing here over time steps in the simulation up to 4 gigayears. So here you're looking at each column of this two-dimensional histogram is showing where I had selected all of the X-bar particles at that time step and then asked about the orbits in that time for those X-bar particles. So you can see over time, we do have a change in the ratio of the frequencies in Z to the frequencies in R, which is the vertical axis there. We're definitely user misaligned. I did not fix that. So this right there is 1. So you see that there's a population of particles that definitely go below the 1-to-1 ratio. There is also, though, a peak around 1, which we're very interested in looking at. And there is a population that kind of spans 0.5 to 1.5, which is a little bit lower of a frequency ratio than we had expected. So that's interesting. You do, though, have the 2 popping out there, which is as expected with the banana orbit family. That's definitely a part of these particles. Quickly compare this now to if you just randomly select particles over the whole simulation. You see the frequency population is definitely different. So X-bar selection is working and grabbing particles that are different than the overall population. But we haven't quantified this in a way that is super meaningful yet. What you're seeing around below 1 gigayear is bar formation. As I mentioned, that was around 0.8 gigayears. You can see kind of the frequency wash that happens there, and then it settles down. So that is interesting to look at. Briefly, just going to show a couple 1-to-1 orbits, just to kind of give you an idea of what we're up against right now. I mean, there's a banana orbit and there's a bezel orbit, but these are supposedly 1-to-1. So we're trying to figure out what's going on here, what this population actually means. Here's a 1-to-1 that looks kind of funky. These are all in the bar frame. There's a lot of interesting stuff to do. So that brings me to my next steps, which we're going to go ahead and figure out what specific mechanisms contribute to this feature, when throughout the formation of the bar does each mechanism contribute, and how can we quantify these in observation. So this is the beginning of a project to me in my mind. I'm very excited about what we're going to do next, and I will offer thanks So quick big thank you to all of the mentors, but especially my own. You guys are amazing. I've really loved working with you and I've learned so much. It's been wonderful, especially my close collaborators again, my peers and my new friends. And that's my summary slide.
Do all boxy peanut bulges have X's?
Probably, yeah. It's so far it's like everything that I found said yes, essentially. But I would, always err on the side of caution. But yeah.
Hello, very nice talk. I was curious, what are some of the things you're hoping that in this project you can really learn about the formation and evolution that you can't do in lower resolution simulations?
So in this high resolution simulation, we have statistics that, because we have such a large number of particles, we have a really high level of statistical significance. When I'm selecting down to the X-bar particles, we get down to like 100,000, I think, or something like that, which when you were to go to higher, so with this higher resolution, simulation, that's smaller selection that we would have to make would be really small on a smaller simulation. And instead, it's still very, very statistically significant population sample that we're able to.
Does the bar rotation rate stay constant through the simulation?
No.
So then you have to follow it with the time-dependent rotation rate as you do.
Yeah. So I just took any. So because we have the location in X, Y, Z, and then also in cylindrical coordinates, I just took the phi and just offset it to 0, and then did the analogous thing in X and Y for all of these. So it's aligned to 0 throughout the simulation. When I'm moving into the bar frame, it doesn't depend on the changing rotation rate. I calculated the pattern speed in order to do that.
And how much it changes in a way in that you can really treat this as an adiabatic family. It's a well-defined family as the bar slows down.
Yeah, so it's changing slowly. So this is we could think about it. The system is changing slowly in comparison to stuff after the bar forms, right? Carrie's going to talk more about this in a minute. So,
cool.
Your question.
Hi, great talk. Do all bars form these boxy peanut structures and just in different strengths, or is it just that there's something different between bars that form them and bars that don't?
So I would say I can't see a reason why the orbits that comprise the boxy peanut bulge would not be in every bar. Like there's no reason that you wouldn't have 2-to-1 orbits, right? But I would say that with bar strength, the strength of this boxy peanut bulge and the X is that's correlated. So I think with a weak bar, you wouldn't necessarily see it, but I'm not confident in that answer.
Okay.
Doing this a couple weeks.
The first is right.
Thanks.
Yeah, but always. Okay. I've done thousands of simulations. I haven't seen one that doesn't have.
Hi, Rachel. Very nice talk. I had this question about, so when you look at this histogram, I see a large population of 1-to-1 resonance orbits, maybe much more than these banana orbits, like 1-to-2 or 1-to-1.5. So my question is, for the X to stand out, don't you expect the banana orbits to be larger in number in the X than 1-to-1?
So yeah. So this is something that we were really surprised to see. But the 1-to-1 pops up really early. And so this is something that if I had more time, I would have sampled just the later population and seen if, how much it is just the 1-to-1. I would it's especially visible, which I don't have it, but with this one, the frequencies that are not 1-to-1 come up later, which is kind of weird because you see them more at the beginning, but we haven't dug into it enough to really have an answer, but that's part of the reason that I did actually pull up some of the 1-to-1 orbits, because those are 1-to-1 and those look like what contribute to the X bar. Those look like bezels and they look like banana orbits. So it's a family of things that are one-to-one plus things that don't look like they should be one-to-one. So I'm trying to figure it out. I don't really have an answer.
Okay.
The Zoom question? I hear we have a question from Zoom.
If you have a question from Zoom, just unmute your microphone and speak.
Okay, thanks for a great talk. Can you please elaborate a bit about the initial conditions of the model?
No, I genuinely don't know the initial conditions very well of this simulation, but there are people in this room who do, and the next talk is going to elaborate on them significantly, I think, or just a
okay.
bit. No.
Sorry. Thank you.
There's a paper though on the archive that you can go read.
So I'm actually not the next talk, which.
Sorry, Kara's not the next talk.
I also don't talk much about the initial conditions, but they match the Woodrow and Dubinsky paper. I don't see Jason, but Jason can elaborate more.